Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to welcome Youngmin Park to Microsoft and to hear his talk. And thanks all of you who are here in person to have braved the weather to come in today. Our visitor won't be here beyond tomorrow, so we're going ahead with the talk anyway. Youngmin is just finished up his PhD work at the Gwangju Institute of Science and Technology in Korea, and he'll be going on soon to work for Qualcomm in Austria in their Augmented Reality lab. So it's great to have him here. He'll be here today and tomorrow, so if you want to talk to him in person while he's here, please come and see me or send me email. I'm Phil Chow, and we'll arrange for you to get together. He's also here with his advisor, Professor Woon-Tak Woo, who's sitting here. And if you want to talk to him, he'll be here as a consulting researcher through the rest of this week. So there's time to talk to him as well. So without further ado, let's hear about some practical aspects of tracking and augmented reality. Thanks.
Thank you for the introduction. Thank you for inviting me and giving a chance to talk. Thank you all for coming here. Okay, let me start the presentation. The title of my talk is 3D Object Tracking for Augmented Reality, Handling Multiple Objects, Motion Blur, and Lack of Texture. Actually, this title is the title of my thesis, so the presentation corresponds to that. I want to begin with a video showing what 3D object tracking is. Here there is no virtual objects, but you can see the coordinate system, which shows that we have the correct pose of the object with respect to the camera. So this the fundamental step required when we want to implement the augmented reality systems. So you can see that with this pose we can put virtual objects that can be registered to this target object. Okay. This is about the needs of the 3D tracking technology for augmented reality. Actually, our lab proposed for the more improved concept than augmented reality, which is UVL. UVL concept is that we believe there is a link between the real object and the virtual object, and it is also possible to interact with the virtual object, or the interaction between human and etc. So the 3D tracking technology is required for the augmentation, which requires actually the 3D pose of the object between the object and the camera. And this slide shows the overall related works. There are frame-to-frame tracking and tracking, the detection of the object from a single scene. We can divide the 3D tracking technologies into two categories like that. And my works are usually concentrated on the frame-to-frame tracking, but I also consider the detection part as well. So there are some mixture of this kind of works. So you can see that there are some challenges for the tracking or detection technologies. The conventional focus was on enabling the tracking natural objects. and there were some more specific challenges that is to improve the accuracy or robustness and the tracking speed. But here I try to find out some more unhandled issues that these are the tracking multiple objects while maintaining the tracking performance. And I also considered the more difficult condition, especially when the object is motion blurred and when the target object is textureless. So the conventional key point based tracking is difficult. So I try to handle these unhandled issues, and these are the main focus of today's talk. So I follow this order. At first, I will talk about tracking the object using the key points that requires complex texture on the object. And in the second part, I will move to the more difficult condition where the object is motion blurred. So the key point extract using the key point is not very easy. And in the final part, I will talk about tracking the textureless object. This is far more difficult. And these are the specific contributions of each part. In the first part, the contribution is about tracking multiple objects while maintaining tracking performance. And the contribution of the second part is to improve the robustness for the motion blurred object tracking. And the contribution of the last part is to enable textureless object tracking. Okay. So this is the first part, multiple 3D object tracking. This video shows the tracking without the natural object tracking. So the focus is on enabling the natural object tracking itself. But when we try to track multiple objects using this kind of technologies, the complexity grows with the number of objects. So if we track 2 objects, then the tracking speed becomes by half. So it is difficult to apply this kind of techniques to handle multiple objects. So our approach starts from simple idea. The detection of the object from a single frame is slower, but it's much robust. And frame-to-frame tracking is much faster, but when we track using this technique, when we track the object using this technique for a long time, then it drifts. So we wanted to combine both approaches to take advantage of them. So what we could do is to detect and track multiple objects without performance degradation. This is the proposed framework and processing flow. Basically, the proposed method run in parallel by 2 separate threads. The first thread handles the object detection, and the second frame handles object tracking frame to frame. So at the first thread, if some object is detected, the information is passed to the second thread, and it handles tracking. Why we divide here these 2, detection and tracking, is that the detection cannot handle many objects. The detection takes more time, so we make the detection smaller, and the tracking is relatively faster, so we can track more objects faster than the detection part. Yeah. how many keyframes are.
Yeah, so you, from the thread 1, you have keyframes you inserted into the tracking thread, right?
Yes.
Just, are you maintaining a cache of keyframes or just...
There's not cache, but here, when I developed this method, actually the detection was very slow. So detecting one object takes most of the time when we want to run it at 30 Hertz. So, I mean, it was very difficult to detect two objects at 30 Hertz. So, there is no cache, but I made the detection problem smaller. So, for example, in the experiment, I considered 12 keyframes. It was not possible to detect 12 objects, all of them at 30 Hertz. So I tried to detect only one keyframe at the frame. Then I passed the detected object information to the second thread. Then the second thread runs much faster because it's frame-to-frame tracking. So even though the detection thread detects one object at a time, we can collect the detected object for several frames. So when you say there were 5 objects detected, then we can track all of them in the second thread at 30 Hertz.
So you keep one keyframe per object?
No, I keep several keyframes.
How many?
Not several, actually, 2 or 3. So there were 7 objects in the database. Okay.
You say that the detection is slow, so when you insert it into the tracking, then maybe the difference between the keyframe and the current frame is already large. How do you track between using the keyframe if the difference is large?
It was possible because we also consider the frame-to-frame tracking. The keyframe is required only for detecting the object, and once it is detected, we track the pose by frame to frame. And this is about some more details. The important thing in the detection part is to keep real-time constraint. So we wanted to distribute the time complexity over consecutive frames. Once we have this, for example, once we have these keyframes in the database, we cannot try to match each keyframe to the input frame if we want to maintain the real-time constraint. So we divided these keyframes into smaller subsets. So we try matching each subset to the one input frame. And okay.
Where the database comes from?
The database.
These are snapshots of the objects you're trying to detect.
Yeah.
Where did they come from?
You have to build it offline. So we have to prepare them before we run tracking. So where it comes from, we take a shot of the object at several viewpoints, and we need to train.
Distance. So how do you scale distance affects, how illumination affects?
I couldn't hear.
I guess I like.
Okay. Actually, I didn't prepare so many slides for this, the first part, because this is a kind of all work for me. So I wanted to skip most part. So if you need some more details, then please read my paper. Okay. So I will explain the key ideas here. And once we detected some objects, we track them frame to frame. And the purpose of this frame to frame is two. The first one is to track every detected object in the image, and the second purpose is to stabilize the pose. So here, for this purpose, we consider temporal key points. These temporal key points are the points that we use for corresponding points between two consecutive frames. And here, the 3D coordinates of these points are not exactly known, so we generate it by ray polygon intersection. Once we have the pose of the object and the model of the object, then we can render the model in the 3D space, and we can cast the ray from the camera center. So in the intersection, we calculate the coordinates. And this is the formulation of the stable frame-to-frame tracking. Here, the aim of this formulation is to find out the pose that minimize the sum of two terms. The first term is the reprojection error between reprojection error of the key points between key frame and input frame. So these are provided at the detection thread. Once we have the keyframe and the pre-trained key points here, and we have the correspondences. So once we project these key points into the input frame using the estimated pose in the detection part, we can calculate the error of each point. So we calculate the sum. And we also have the matches between previous and current frame. So here we also can calculate the reprojection error, but these points are the temporal key points, and the exact 3D coordinates of these points are not known. So we consider weights for each key points. That's here. So finally, this constitute the error term. So we try to find out the pose parameters that minimize this sum of error.
Question.
Yeah.
Find the point-to-point correspondence.
How do I find the frame-to-frame correspondences?
The point-to-point. You have those points, right? So between the current frame to keyframe or current frame to the previous frame, so you have those correspondences there.
Yeah. How do I find the correspondences? Actually, we need different approaches for finding out the matches between keyframe and current frame and previous frame to current frame. The finding match between previous and current frame is much easier because we can assume some constraints. Here, for example, we can say that the object pose is almost similar between two frames because the object cannot move so fast. And so the matching between two consecutive frames is much easier. Here we can just extract some corner points, and here we can also extract the corner points. Then we can find we can calculate the correlation between key points. For example, we want to find out the correspondences of this point at this frame. Here we can check here the key points around the code, around this key point. So we calculate the correlations between them. So we can choose the one with the highest correlation. It's simple one, and then finding out the match between the keyframe and current frame is most difficult. It is actually the problem of the detection algorithm. Here we cannot assume that the kind of things we applied here, finding out the matches between previous and current frame, because the pose can be much different in this case. And actually, in the implementation, I just adopted the algorithm developed in other institute, developed in Civil Lab, EPFL. And there are many other methods, for example, SIFT or SUF. They are very famous and used frequently. But I think it is difficult to explain them here all. Okay, so and I want to skip the part that about calculating the weights, because it is far more details. And I want to show the result. In the experiment, I considered 12 keyframes, and I explained the subset. But in one subset, there is only one keyframe. So it's the video. Here for the detection, we use the Ferns method developed in Civil Lab EPFL, and it can detect one keyframe at about 40 Hz in our PC. So you can see, even though the detection speed is slow, but we can handle multiple object tracking like that.
They have to be planar to be detected?
No.
Okay, I guess those are on the box.
Yep. It was because we need the model of the object. So obtaining the model is difficult. So I just used the box type objects here. And this is the important result to show the frame rate. We run two threads, one for detection and one for frame-to-frame tracking. Here, this is important that the frame rate of the detection part is maintained at about 40 Hz. The number is not important, but you can see it is maintained almost the same. And in the database, there are several keyframes. So you can see the detection speed is not affected by the number of keyframes. And you can see the frame-to-frame tracking runs faster than the detection, even though it handles more than one object. You can see the number of objects tracked in each frame at here. Okay. And the discussion for the first part, the advantage was that the proposed framework is general, so we can adopt any other methods using this framework. For example, in the implementation, we used the Ferns method, but we can also use SIFT or something others. And the performance is good when the key points are very well extracted, and it runs fast and robust. But there are limitations. For example, the object tracking depends on the key points. So if we cannot extract very good key points, then we cannot track the objects. So we move to the second part, tracking objects on the motion blur. The motivation is explained in the previous slide. This picture shows the corners extracted from this frame. You can see when this object moves fast, so it is captured with motion blur. Then the corner points are extracted at some point, at some reason, but you can guess these are just useless. And here in this part, there is no available key points. So tracking this object using key point based method is very difficult. So what we do here is to consider template-based tracking approach. The advantage of template-based tracking is that you can track objects without feature extraction step. So there is possibility that we can track the object when feature extraction is not available. Here, this picture shows the overview of the template-based tracking. This is the template of the book we want to track. And you can see this is the captured image. Then we can predict the pose of the object. So we can warp. Once we warp this template with the predicted pose, this could look similar. So the aim of the template-based tracking is to find out the pose that minimize the difference between the warped image and the captured image. So this provides the pose of the target. But this can be limited because the image formation model, which corresponds to simple image warping, is very limited. You can see this is the picture. This is the captured image of the moving object. So you can see the motion blur here. And this is the rendered image with a predicted pose. Then you can see the difference is very much by the motion blur. And this is the result of the standard image formation model. So here we proposed generalized image formation model that considers there exists motion blur. So you can see this is the rendered image using the proposed image formation model. Then the difference becomes much smaller when you compare it to the previous one. This proposed model considers that the object can move during the time when the camera shutter is open. So this model simulate the motion blur like this way. So what we do here is to derive this image formation model to an optimization problem, which will be not happy for you. So I want to skip, but
What is theta?
Huh?
So theta is an angle or a rotation matrix, or what is that?
Theta?
Theta. Theta? The parameter.
Theta.
Theta.
Theta. That is the camera pose parameters. The rotation and translation. I need to say that we adopt the efficient second-order minimization approach, which is also a template-based tracking approach. Let me skip this one, and here I can show you the derived solution is we named it ESM blur because we consider motion blur. So this J blur matrix is important. The A coefficient here is about the shutter open and close time. So when the shutter speed is very fast, then so the exposure is infinitesimal, then A becomes 1. So when you put when you put 1 into here, then you can see this J matrix becomes that of ESM method. And when the exposure time is very long, so when we guess the maximal exposure, the A coefficient becomes 0.5. So this is the bound that the parameter can vary. And to run this ESM blur, we need to we need to select manually the parameter A. So you wanted to skip that. So we also try to estimate the A parameter automatically. And it requires the estimation of the shutter speed at each frame. And this derived to some bigger J matrix by the augmentation of the one additional term. So we named it here ESM blur SE, and I also want to skip this part. And
But is there an intuition about what you're optimizing A? So is there an intuition about what you're doing to find the optimal there? Like trying to match the blur somehow, or?
Try to estimate the A.
Yeah.
Okay.
What is?
Okay.
There's no intuition of mine.
A actually appears from the proposed image formation model. In the image formation model, there were two timing, T0 and T1. They are the shutter open and close time. And by the derivation, A becomes like this. That means we can also compute the partial derivative with respect to this A term.
Maybe to explain what the T0 and T1 means. I guess the opening and closing of the shutter? Or?
Yes. Okay. At its frame, when its frame is captured, there is moment that the shutter is open and closed. And the proposed model considered that two moments.
So you try to find those first, and then you get what A is, or?
Yeah.
And you find those how?
Yeah. At first, we replace the T1 term by number 1 because we want to simplify this problem. So we estimate only one parameter than 2. So we replace T1, the shutter close time, by 1, and then we normalize the time. So we have to estimate only one parameter then. Then we derive the equation, not explained in the previous slide, but when you derive that, we get this kind of equation. And
so you're basically trying to do matching of the observed image to the synthesized image, or?
No, we try to solve that only in the formulation. So we do not render using some estimated parameter and calculate the difference. We do not run that kind of things, and we just derive in the equations, and that could give some solution. Okay, I think you have to read my paper for more details.
I just thought there might be one sentence intuition.
I still have 40 more slides. So I couldn't put everything here. Okay. And the template-based tracking is still a frame-to-frame tracking, so we need an initialization, which is actually detection. So for automatic initialization, we used Fon's method to detect the object and estimate the initial pose. And it is also needed, we need to check the failure of tracking. This can be found when the correlation between template and the input image becomes too lower. And these are the results. Here, this video shows the comparison of the tracking performance between ESM, the previous one, and ESM Blur SE. At the moment that tracking is failed, the image becomes red. So you can see when and how frequently the tracking fails. Here I move the object fast, so the motion blur becomes heavy, and the shutter speed of the camera is auto-adjusted here.
So what happens when the tracking fails? You just can't superimpose this object on top properly? I mean, it recovers afterwards, right?
Yeah. Once the tracking fails, we try to detect it again, but it is not available until the motion blur becomes very small. So
Right, but when he's like throwing the box, maybe it doesn't. I mean, is there a consequence of failure? I mean, maybe it doesn't matter if you accurately post the augmentation on the box when you can't see any details. Or
Well, if we fail tracking, then the augmented contents disappear.
right. Is that a problem?
That's very annoying situation.
Okay.
I mean, because we try
It seems pretty extreme, but
what we are trying to do is we observe some blurring, still we keep tracking. Also, we apply the blurring effect to the rendering.
I see.
the aim is to maintain the tracking, so we want to avoid the discontinuity of the augmentation. This is about augmentation that simulate the motion blur. I want to skip this part. I didn't explain that either in the slides. And I performed a synthetic experiment because I wanted to get some statistical results, statistical comparison between the previous and proposed method. I exploited 3 templates and synthetically generated the motion blurred image by increasing motion and some restrictions to the motion. I generated 3 different cases. The first one is translation only, and the second one is rotation only, and the last one is the combination of rotation and translation. So I wanted to see what is the average result. So at first, about the robustness, I increased the motion gradually, and I'll experimented for translation, rotation, and the combination. Here you can see the ESM, the previous one. The success rate of the previous one becomes lower when the extent of the motion becomes large. But the proposed method maintain more success rate. So you can see the difference becomes very large at this point, and almost double. And it's almost the same for the different motions. So here you can see the robustness is improved.
Larger motion means severe, more blur in the capture image.
Yes, usually. Here you also need to consider the exposure time. It was random at this experiment. So if the motion is larger, then it can generate heavier motion blur. And I also measure the time and accuracy, and this graph says that the proposed method requires less time, but the accuracy is slightly better. And this picture shows the result for the real sequence, not the synthetic images. The first row shows the tracking result of the ESM method. I put the results at the moment when ESM fails, actually. And at this moment, the ESM blur succeed to track, but it requires many iterations for the pose estimation. But the ESM blur SE succeeds as well, but it requires less iterations. So, and the statistics of the comparison for the real sequences. These tables say that the proposed methods tracked more frames and spent less iterations. The coherent result. And the computation time. Actually, the template, this could be faster if you adjust the size of the template, but the average tracking time of the ESM was 4.7 milliseconds for a frame, and ESM blur and ESM blur SE, these are faster. And here you can see ESM blur SE is a bit slower than the ESM blur, but at the result it shows this one is more robust. So the conclusion here that if we need faster algorithm, then we can adopt ESM blur, and if we need more robustness, then we can use ESM blur SE. And the discussion for this second part, the advantage is that we could track the objects on the motion blur. So when the key point extraction is not available, then we could still run the tracking. But here the discussion point is that we still requires texture on the object. So we move to the last part. This one is textureless object tracking. Okay.
So from the user experience, if you start from the clear and blur and go back to the clear, and only in the middle part, when it's blurred, will affect the user's experience, right? So I'm just wondering, have you compared the ESM algorithm and your algorithm to figure out the difference in the continuous way to figure out, for example, from clear, blur, and clear, and ESM, the gap for the ESM failed to track is, for example, 100 millisecond, and your algorithm, the gap is smaller than that, maybe 50 milliseconds. Have you compared in this way to figure out the, compare the gap? What's the improvement in terms of the gap?
I actually didn't measure that, but I can say.
Because you compare the overall number of the frames is filled or not. But for example, if every 2 frames you drop 1 frame, that will not affect user experience that much. But the gap, because sometimes blur, when the blur stops, it's become clear, and the augmented stuff need to be clear instantly. That part really affect the user's experience.
That's a good point.
Yeah. In the tracking aspect, when the tracking fails because the motion is too large or the motion blur is too heavy, then this is the moment when the object moves very fast. So the tracking fail, and it requires some time until we can recover that. That is the moment when motion blur becomes small. So the number of failure here doesn't show the, how frequently the tracking fails. So how frequently the tracking is interrupted. But here I can say by this characteristics I just said, that when the tracking fails, it requires time until it can be recovered. The number of number of tracked frames can infer that how often the tracking was interrupted. And
yeah, I understood. My point is in the middle, because the image is very blurred. If you fail, I don't care because I cannot tell that. But when the image from the blur too clear at that point, that fail really make me feel that you for example your augmented stuff, virtual stuff.
What he didn't do that until now, because that might be next experiment.
Okay. So that's cool.
So you basically can apply different weights on different type of failure.
Actually, he did the experiment, but he didn't analyze that part.
okay.
Thanks.
Okay. So we move to the last part. This one is very recent work, this last year. So this is about textureless object tracking, and in this part especially I used Microsoft Kinect. So I think this is right place to present this one. And this video is about the result. I will explain later, but we train this object on the fly, and we track that at the same time. And this kind of object is very difficult to detect or track by using key point based method or something others. So I will go into the details. The challenges of tracking textureless objects are mainly two. The first one is that we need the model of the object, and the second one is we need the initial pose of the object. So this one is all work, but very important in this area. This kind of textureless object can be tracked, but here we need to obtain this complex model offline, and we need to manually provide the rough initial pose. So we need to solve these problems. At first, obtaining this 3D model can be done by this kind of online model generation. Here, the user rotates the object slightly, and the model is automatically generated online. But here, you can see this requires the key point tracking, so there must be complex texture on the object surface. So this doesn't fit to my purpose, tracking textureless object. And this one is template detection method. Here you can see this object is very small and textureless, but it is detected almost real time. But this method provides the template index and 2D image position, not the 3D pose which we need. So this kind of works cannot be applied to my purpose, and and here I need Microsoft Kinect, the RGB camera. The good point of this Kinect is that it provides the depth information on textureless area. As you can see here, the box is totally textureless, but the depth information for this box is obtained. This is not available by the stereo vision approaches, mostly. So the proposed approach is training while tracking. At first, we need a simple setup here. We put a known pattern or marker to define the world coordinate system, and we define the position of the object you want to train or track and the rough bounding box of that object. And then we can run the frame-to-frame tracking with the information obtained in the first frame. So this is the training. We move the camera around the object and observe the object. Then the templates and pose of the templates, the information required for detection and tracking are obtained online. So this picture shows the templates, the viewpoint of the templates. This picture shows the training stage. At the very beginning, the camera is at random position, but it observes the target object. And here is a known pattern, so we can compute the pose of the pattern with respect to the camera. And we need to specify the position and rough size of the object. It is not very complex. Then we can obtain the template of the object and the pose as well from the pose of the pattern, because we know the relation between the pattern and object. Then we can move the camera, and at some moment, if this the system determines that additional template is required, then it is added, and the pose is also recorded. It is repeated until we finish the training. So here what we need is the criteria to determine if additional template is required or not. We define two criteria. One is the minimum rotation step. At each frame, we assume we have the pose of the object. Then we can compare the current pose with the previously obtained pose. And if the rotation is very much different from any of the previously obtained pose, then we need to add another template at that moment. And the second one is detection score. For the detection, we exploited DOT method, and At each frame, we try to detect that object using the DOT method, and if the detection score is very low, then we need another template. So
So you already have the depth information. These templates are 2D, right? Why you still want to use the 2D information? You have 3D there.
yeah, the depth map is required to compute the 3D pose. Using the color image, we can detect the object, but it is really difficult to compute the 3D pose because there is no given object model. The information is very limited, so we cannot calculate the pose.
The question is, why do you need the 2D templates?
Why do I need 2D templates? That is for detecting that object. So we use two kind of templates. One is the template obtained from the color image, and another one is template obtained from depth map. So using the templates from the color image, we detect that object. The color image provides the appearance of the object, and the depth map, using the template from the depth map, we can calculate the 3D pose. So here we need both.
Seems like there might be alternative and more direct means. If you've got the three-dimensional geometry, then it seems maybe you just need one 3D template instead of a lot of 2D templates.
Yeah, the depth map also can be used for the detection as well. It's just I couldn't.
But instead of getting a whole, you're collecting a whole bunch of templates, right?
Yes.
So that you can recognize it from any direction or whatever. Right?
Yeah.
But maybe you just need one 3D template instead of a whole bunch of.
To do that, we may need a method to match the 3D model to the single view.
Yeah.
Maybe it is also possible, but well.
Maybe using moments or other things.
Yeah. If it's possible, they can be better. So I continue. This picture shows the training result. The training started at this point and moved following this trajectory. And the blue square shows when the templates are added. And
Using the 3D template only depth information is that it is very difficult to identify two objects which has very similar shapes like the buttons. They all look alike.
Well, I mean, you'd have to have color too.
Oh yes. But in that case, it's not that much different. Like you just take a 2D element.
Yeah, it's just it just looks like you're collecting a lot more information than maybe you need.
Yeah.
So basically,
both are the same. 3D model, geometrical model, and the texture information is the geometrical model and the two-dimensional keyframe. Two-dimensional keyframe is just that projection of the 3D model with the texture.
the basic idea here, we're trying to figure out the sparse representation over the entire trajectory, right? But what I think Phil said, it's the sparsest representation, it's the 3D representation. And that's the sparsest, you only have one model to represent the object.
All right. Ideally, there is the right direction. In order to speed up the process, we don't need to calculate the exact 3D texture model. We just capture the 2D images, then we use them as template.
You keep adding the template.
Keep adding the template.
You estimate
3D model. That is 3D model. Yeah.
I understand, but why not estimate, after the whole trajectory is done, and then you figure out where the template should come from? because here you keep adding, so I think the number of the templates will be more than if you consider the whole trajectory together and figure out where is the best place you should have the template over there.
As far as I know, it's really difficult. We need to compare the image that is from only one limited view, and we have the 3D structure of the object. The matching between the 3D structure and the image is, as far as I know, it's very difficult. That's the problem.
the same thing. I think. Basically, both approaches are exactly the same.
So I think if you have like a 3D model, you could project back, as you say, to particular locations, and you would get something similar, but it wouldn't be the same if the object is not working. The way you do, you actually capture reflections and
compensate for specularity.
Right.
There is another difficult process. We just skip that part. Just use the 3D geometrical model and then capture the 2D images. That is much easier approach.
Okay. So I continue. After training, what we have is the template and pose of the object from various viewpoints. But when you detected the object at some point, it is possible that we cannot use the pose of the template, pose corresponding to template directly. What I mean here is that, let's say we have the template captured at this point in the image, and we have the corresponding pose at the moment of the object. But it is possible that this template can be detected at another position in the image. So, in this case, the obtained pose of the object cannot be applied directly, so we need to compensate it. Here, what we can exploit is the position of the template detected, the position of the template obtained and detected. So we can compute this translation in the image, and once we have the camera parameters, we can calculate the translation in 3D space. So we can compensate this pose, and it becomes closer to the actual position, actual pose of the object. And after the detection, we need to compute a 3D pose, exact pose. Here, the pose estimation is done by two steps. The first step is ICP algorithm. This algorithm calculates the motion between 2 point clouds. So I exploit that to refine the initial pose provided from the detection. But we also observed that this pose could be improved by the second step. Here we exploited edge-based method to further refine this pose. But here we don't have every information required to run the edge-based method. So so we replace some of the steps. For to run this edge-based method, we need the control points, some sparse points following the edges, and we also need the normal vector at each of these points. But we don't have the normal vector here, so we consider the nearby pixels of that control points and replace the direction of the normal vector by this vector perpendicular to neighboring two points. This one is far more details. And we also do some depth map enhancement. The purpose is to reduce the noise of the raw depth map obtained by the Kinect. Here you can see the edge is unstable and it's not feasible, but the surface is also unstable. So we can say the noise in two ways. The first is the noise around the object boundary, and the second one is the noise on the object surface. So we try to enhance this raw depth map by image filtering. At first, we divide the depth map into two parts, the boundary region and the superficial region. So we apply different methods for each of them. For the superficial region, we just apply the bilateral filter to the depth map, but because the smoothing the surface seems enough. And for the boundary region, we developed another method. Let's say this is the real object, the appearance of the real object, and this is captured at the color image and depth map like this. And we focus on this pixel. In the color image, this pixel is captured very accurately, but in the depth map by the boundary noise, we can say sometimes this the depth value of this pixel is missing. So we try to get the proper depth value for this pixel by considering the nearby other pixels. This is the formulation. This is a kind of joint bilateral filter. We consider the intensity difference between the central point and nearby pixels. And we also consider the distance of each pixel, and we put the depth value from the depth map. Then what we get here is the reliable, we call it reliable depth corresponding to this pixel. So the meaning of this formulation is that we collect the depth values from the nearby pixels and determine weight of each pixel by observing the color image. So the depth value of the pixels that the intensity difference is small has higher weight, and once we collect them, then it becomes it could be the depth value of this pixel. So this is the more formulate the equations, and you can also read my paper. And this is the result of the depth map enhancement. This is the raw depth map, and the boundary is unstable, but by the enhancement, the boundary becomes clear like this, and it can be overlaid clearly on the color image. And the noise on the superficial region looked like this, and by the smoothing effect, the noise becomes smaller. And this, yeah.
So we know you collect the different distance these uncertainties. How did you apply these characteristics into your surface enhancement?
Are you asking how to differentiate both regions?
So when the surface is closer, you have the standard deviations of the noise is less than when the distance is farther. You try to apply these characteristics into your enhancement.
I didn't consider that, but it would be valuable to measure how the noise happens according to the distance. It may be a very good point, but I didn't do such things.
There is not our technical contribution, just used the existing method.
The depth and the color camera are slightly offset. Did that cause a problem on your edge alignment?
Yeah. So, but here we have the 3D coordinates of the depth map. I can show this. I can show you this picture. This one is not actually the raw depth map, but this one is transformed to be corresponding to the color image. So these parts are missing. This means actually the focal length of the depth, the IR camera for depth estimation is a bit larger. So the picture is actually smaller. So by the transformation, it became some parts are missing. So it is we need to transform each depth map to another coordinate system. The camera coordinates of the color image. Yeah.
Did you use the vector integration or did you recalibrate it yourself?
Sorry, I couldn't hear. I couldn't hear.
Did you use the factory calibration or did you recalibrate that?
I calibrated that. There was some method. I captured the pattern through the color camera and the IR view. So I calibrate that.
But anyway, this one is not the optimized method. If we use the new algorithm developed by Microsoft and the UCL people, we can get more smooth and accurate depths maps, and we can apply that onto our algorithm.
Okay, so I continue. This is the result video. Okay. So this is the training phase. The blue square shows the template size, and at some moments the templates are obtained. And this is the training phase. Here we can move the object, and this shows the tracking when the object is partially occluded.
So how did you? I guess you're using Kinect to occlude the. You're occluding the red, the axes. I guess you. How do you do that?
That's why we use the Kinect.
Okay.
Actually, this is not 3D rendering, but I draw the dots in 3D space. I mean 2D space, but I can check the visibility from the depth map.
In the video, you initialize the camera's pose at the beginning,
Yeah.
and then remove it, and then get a set of templates. In that process, you may have some errors accumulated during the errors in the pose of the camera when you move the camera to capture pose, because you estimate the current frame's pose from the previous frame. Don't you have such kind of errors?
Use keyframes. Helps.
Yes, errors there can be error. Actually, I compute the pose with the previously obtained template and the depth map, input depth map. So it's a bit different from frame to frame. So the drift must be less. But there could be still error, but you try to optimize that. Okay. And this is another video, the cactus. Actually, after recording this video, this cactus tried to die, so I cannot obtain another sequence of this. Okay. Oh, sorry. Oh. And this object is very complex, so maybe obtaining the model must be really difficult. But we could skip the part and track. And this one again. Actually, the difficulty of detecting or tracking this kind of object is that there are some holes, so the other side is visible through this object. So by using the key points, the appearance of the key points must be different in actual situation. So this one is very good example. And some result of the pose estimation, I want to explain it simple. The red one is excuse me. I projected these points by obtaining the pose of the stationary object with the stationary camera. So if the pose estimation is very good, the projection of a specific point must be a single point. So here I show the distribution of the points. So the red area shows the pose estimation by the raw depth map and the conventional ICP. And this one shows the result of the enhanced depth map and the proposed pose estimation. So here you can see the distribution is much smaller, so we can say the pose estimation is stable. Oh. Okay. And these are some numbers. But this one also says the jitter of the pose estimation was reduced by 20 to 30%. Yep.
Compared to green one and the blue one, and the variation along the y-axis is almost the same.
Yeah.
But the major difference is along the x-axis. Do you know why?
That is actually a very good point. Here, the variation is smaller, but the mean is different. So here I can say this one is because of the second step of the pose estimation. it considers the color image, not only the depth map. So we do the calibration of the depth map, calibration between depth map and color image, but it cannot be exact. So there must be some displacement. So once we consider that the color image at the pose estimation, that can give some translation. But we believe that becomes more accurate pose, we believe. But it's really difficult to measure difficult to measure the accuracy without the ground truth data. Anyway, the displacements happens because of the consideration of the color image. That's very good questions. And the computation time. When you run the detection and tracking, both of the detection and tracking, it takes about 30 milliseconds, so it can run at 30 hertz. So I can say it is real time. But the frame-to-frame path requires about 13 milliseconds, so it may handle up to 3 objects at 30 hertz. So the conclusion, we implemented real the textureless object tracking, which doesn't require pre-built 3D model. And we also proposed depth map enhancement. And the future must be about the scalability of the detection part. And it'll be also good if we can estimate the pose without the depth information. And this is the end of long presentation.
Thank you very much.
So, do you have any other questions or comments?
So, the title is about augmented reality. Most of that is tracking. Just see how the tracked information can play a more accurate role, active role in rendering.
Can you hear the last part?
Instead of rendering, we have to attach contents to the object. In order to attach 3D contents to the physical object, the detection and tracking is pretty much important. That is the first step of the augmented reality.
That's a requirement. Is any needs, because I'm inexperienced. So I would just say, for the sake of augmented reality, is that we know tracking usually are not stable due to
His focus is tracking for augmented reality, not augmented reality itself.
Yes, that is that.
I guess the question is, if you're doing something specific as augmented reality with the tracking, can you, because you didn't seem to exploit the fact that you're using the tracking for the augmented reality, is there anything you can do? Maybe the answer is no.
Yes.
Is there anything
Thank
that
you. That's my question, actually. I just try to see the linkage. So,
We can do actually, we may do several things using 3D tracking, but here, why my title is 3D tracking for augmented reality is that usually the main application of 3D tracking is augmented reality, and this is very attractive application actually. So I say that. But it is also possible to use the tracking information for user interface. For example, tangible user interface. You need to track the objects for interaction. So it is also possible. But here my target is augmented reality.
Okay, great. Well, thank you very much.
Thank you.